So hello everyone, this is a weekly review from YT Help dated from 7/1/21 to 15/1/21 of the course TDCM, that is transformer and the DC machines. So topics covered so far are the DC machine, that is the electromechanical energy conversion, the excitation, the types of excitation, and the basic definition related to the DC machines. Singly excited system and the doubly excited systems. The single phase transformer, its construction and its types of transformer. Now, electromechanical energy conversion. So the device which converts the electrical energy to mechanical energy or vice versa is known as the electromechanical energy conversion. So therefore, when a coil is applied a voltage and the current flows through it, it is known as an excitation. Based upon this excitation, there are two types of system possible, which are known as the singly excited system and the doubly excited system. Basic definitions related to this DC machines are like permeability, it is the amount of ability to pass the flux. Reluctance, it is the resistance offered to the flow of the coil. Generally, air has the highest resistance reluctance. That's why the leakage flux is well less and it provides a very high amount of efficiency. Now, based upon the excitation, two types of excited system are possible. That is the singly excited system and the doubly excited system. So, therefore, as per the word suggests, the singly, that only a one coil is required to produce a magnetic field. Similarly, the word doubly, it suggests that two coils are required to produce the net mechanical output force. Now here in a singly excited system, only a one electrical input is there and it generates a one mechanical output terminal. Similarly, in a doubly excited system, two electrical inputs V1 and V2 are there and it generates a one set of mechanical output terminal in the system. Now the examples of a singly excited system are this electromagnetic relay, the solenoid coil, the hysteresis motor, etc. Whereas the examples of doubly excited system are the synchronous motors, alternators, DC machines, etc. Now, a single phase transformer. Basically, a transformer is used as a device that is used to reduce or increase the voltage level. Basically, in a transformer, a generating station is the generating station generates about, let us say, 11 kV of voltage. Now we want that 11 kV to be transmitted directly to the distribution sector to be used. But while transmitting directly to the distribution sector, there would be a power loss or a heat loss possible. So therefore, transformers are transformer basically of two types. That is of a step up transformer and a step down transformer. Step up means increases the voltage level and step down means decreases the voltage level. So when a generating station and 11 kV voltage is generated, so first of all the voltage is stepped up. So therefore it makes up to 40 kilovolt. Now this 40 kilovolt is then transferred to the transmission line, and this transmission line again at a step down transformer is used. We want 11 kV to be distributed to the distribution sector. So therefore the step down transformer steps down the voltage to 11 kV. So this is some basic application where a transformer can be used. Now coming to the topic of a single phase transformer. So this figure shows a single phase transformer. In this, the magnetic core, laminated core is shown by the gray color. The green color shows the primary winding, whereas the red color shows the secondary winding. And alternating voltage is applied onto the primary winding, whereas a load terminal is connected across the secondary winding, across which the terminal voltage, let us say V2, is to be measured. E1 and E2 are the primary and the secondary EMF generated. N1 and N2 are the number of turns in the primary and the secondary winding. I1 and I2 are the primary and the secondary current corresponding to the primary and the secondary windings. Now the alternating voltage is applied, and so the current would be alternating. And also here, due to the high permeability, for an example, let us take an example of a silicon. So therefore, alternating flux would be generated. Now let us say that N1 are the number of turns in the primary winding. So due to this number of turns and the alternating current, the flux links with the number of turns with the coil due to the Faraday's law, and an induced EMF is generated in the primary coil, that is denoted by E1, which is equal to minus N1 d phi by dt. Now, similarly, the flux links with the secondary winding and the turns, and so therefore, by Faraday's law, we can say that the secondary induced EMF is generated, that is known as a minus N2 d phi by dt. Now, we are from this figure, we can say that the same flux is linked with the primary winding and the secondary winding. So, therefore, if the same flux is there, so therefore d phi by dt in both the cases, that is in primary and secondary EMF, would be same. And so, therefore, we can say that E2 by E1 is equal to N2 by N1. Now, Let us take for an instant that the number of turns of the secondary winding is greater than number of turns in the primary winding. So according to the Faraday's law, E1 equal to minus N1 d phi by dt. So now if the flux remains constant in both the primary and the secondary winding, so we can say that the EMF generated is directly proportional to the number of turns. So therefore we can say that the induced EMF is greater than the uh, primary EMF, that is second EMF greater than the primary EMF, that is E2 is greater than E1, and so therefore the terminal voltage V2 would be greater than the supply voltage, that is V2 will be greater than V1. So if V2 is greater than the V1, then the voltage is stepped up while transferring from the primary winding to the secondary winding. The reverse is the case of for a step down transformer. So if the number of turns in the primary winding is greater than the number of turns in the secondary winding, and according to the Faraday's law, that is the induced EMF is proportional to the number of turns if the flux remains constant. So therefore, the induced EMF in the primary winding would be greater than the induced EMF into the secondary winding, and so therefore the supply voltage will be greater than the terminal voltage. And by transferring from the primary winding to the secondary winding, the voltage is lower down. That is, the voltage is stepped down. That is known as a step down transformer. Now this is a symbolic representation of a transformer. Here supply voltage V1 is there and the terminal voltage V2 is there. Current I1 is flowing through the primary winding, I2 is flowing through the secondary winding. This is the primary winding, this is the secondary winding having turns N1 and 2. Now here the power is transferred from the primary winding to the secondary winding. Here in both the primary and the secondary windings, the V and IR remain different, but the frequency of the power always remains same. Here there is no electrical connection between the primary winding and the secondary winding. So here the primary winding and the secondary winding are connected during by the mutual connection. That is, one coil excites the another coil. Now there are resistance into the winding, and so therefore copper loss I square R is present into this winding. Talking about the efficiency, also in this transformer core is made of, for example, is made of silicon, so therefore it would have alternating flux link unique, and so therefore it would have iron loss in it. It is an eddy current loss in it. So this loss is generally a very less, so therefore efficiency is very high. Also, a transformer is regarded as a static machine, so therefore it does not have any rotational part in it, and so therefore it avoids the frictional losses in it. So therefore the efficiency of transformer is regarded to as 97% to 99%, and it is nearly transfers the same power from the primary winding to the secondary winding. It is from the primary part to the secondary part of a transformer. Now, basically, a transformer is constructed in a two ways. It is the core type transformer and a shell type transformer. The first figure shows a core type transformer, and the second figure shows a shell type transformer. In a core type transformer, a magnetic laminated core is taken over here, having a flux generated phi in it, and here the upper part of this core is known as the and the lower part of the core, that is the upper horizontal and the lower horizontal part, is known as the yoke, and the vertical part is known as the limb. This is the left side of limb. This is known as the right side of limb. Now, similarly, if case goes with the shell type transformer. It is the upper horizontal part. Upper horizontal part is known as the upper yoke, and the lower horizontal part is known as the lower yoke of the magnetic core. And the vertical part are known as the limb. This is known as the left side of the limb. This is known as the central limb, and this is known as the right side limb. Now here LV winding and HV windings are wound around the core. For an example, in the core type transformer, along the left side of limb and the right side of the limb, generally the LV windings are wound near to the core, and HV windings are on the LV winding, that is they are very away from the core. Now here LV windings are kept very near to the core, so therefore the insulation required would be very less. That is, less insulation is required. Now, for an instance, let us think that the HV winding are kept very near to the core, that is, LV windings are kept on HV winding. So, therefore, the flux linkage would be much more, and hence the coupling capacity would be very less. And so, therefore, amount of insulation would be required must be much higher, and therefore, cost would be increasing. Now, if LV winding is an HV winding, the flux linkage improves, and the flux linkage would be less, and hence less insulation would be required, and just reducing the cost. Now coming to the shell type transformer. In the shell type transformer, the LV winding and the HV windings that the LV windings and HV windings are kept one below the other, and alternate LV winding and HV windings are kept like first layer of LV and HV, LV, HV, LV, and a sandwich type construction is generated. The LV windings are kept at the place near to the yoke so that the proper and less insulation is required, and when one winding excites, it produces a flux phi in the central limb. Now this flux phi produced in this central limit divides into two parts, that is 5 by 2 and 5 by 2 in the left side and the right side of the limb respectively. Now this flux thus produced offers a low reluctance part to the magnetic field, and hence the flux flows. In this windings, we are talking about the shell type and the core type transformer. The shell type transformer, the windings are surrounded by the core, whereas in the core type transformer, the core is surrounded by the windings. This is one of the major difference between the core type transformer and a shell type transformer. Basically, the shell type transformer are used in a low voltage part, it is in electronics part. In this, it is difficult to handle because if the fault comes, and the fault cannot be easily observed since the windings are not directly visible. Whereas a core-type transformer, it is used in a distribution part, in a large application distribution transformer. It is used in a high voltage part. So if a fault is there, then the fault can be easily identified since the windings are easily visible in a core-type transformer. Thank you.